Problem 4.10. A sphere of radius big R carries a polarization P of R equals KR. A. Calculate the bound charges, and B. Find the field inside and outside the sphere. So first, to calculate the bound charges, we can use equations 4.11 and 4.12. First, the volume charge. The volume charge density is equal to the negative divergence of the polarization per unit volume. Polarization per unit volume is given as K times R. This is using spherical coordinates. So looking up the spherical coordinates, we see that our polarization vector only has an R component. It does not have a theta or a phi component. And that R component is equal to K times R. Recall the rules for calculating the divergence in spherical coordinates, looking only at the radial term. If our radial component is KR, then our divergence is 1 over R squared times the derivative of KR cubed. Take the derivative of KR cubed, we get 3KR squared times 1 over R squared. We are left with 3K. Also remembering that equation 4.12 has that negative sign, the bound charge density inside the sphere is equal to negative 3K. Next, let's look at the surface charge. From equation 4.11, the bound surface charge is equal to P dot in hat. Since we are looking at a sphere, over the surface, the in hat vector is equal to the R hat vector. Also at the surface, we would say that the R vector is equal in magnitude to big R and is in the R hat direction. So R hat, or KR R hat dot R hat, the R hat dot R hat becomes 1. And so the bound surface charge is equal to K times R. Part B, find the field inside and outside the sphere. We could do this through integration, but we've seen a problem like this before. This is a sphere with a constant charge density. So we can probably more easily use Gauss's law to solve this. So recall Gauss's law. The total surface integral of the electric field is equal to 1 over epsilon naught times the total enclosed charge. For a spherical Gaussian shell that is inside the sphere, we can say that the left-hand side of Gauss's law, since we're assuming radial symmetry, electric field will depend only on R, and so E of R times 4 pi R squared. And again, since the volume charge density is a constant negative 3K, we can say that the total, that the total enclosed charge is equal to that charge density times the volume of 4/3 pi R cubed. Put that together, and we get that the total electric field inside the sphere is equal to rho R over 3, I keep forgetting that epsilon naught, which, since the charge density was negative 3K, that 3 cancels. And so the electric field inside the sphere is equal to negative KR over epsilon naught. Outside the sphere, we could do something similar. We would integrate over all of the volume, But the outside for the outside, or for the region outside the sphere, we would also need to include the charge on the surface of the sphere. And it turns out that if we integrate this volume charge over the entire sphere, and this surface charge over the entire surface of the sphere, they add up to 0. No net enclosed charge, and again, because we see that this system is radially symmetric, that means no electric field.